So our next session is Science Enabling Human Space Exploration. This panel will explore our current understanding of the hostile space radiation environment, our current observational, modeling, and predictive space weather capabilities, and the translation of these capabilities to operations that enable safe human interplanetary exploration. Go ahead, come on in, please. The establishment of a permanent presence on the moon and eventually Mars, and the safeguarding of our increasingly space-dependent technological society. So as we finish getting this one set up, please do stick around for this session, and then we'll take a short break, and then we'll come back after that to talk about lunar logistics. And please don't miss our luncheon keynote, and we have some awards to present over there in the Student Services building. So it's looking like this group is pretty much set. And so with that, I will turn it over to our moderator, David McKenzie, supervisory physical scientist here at NASA's Marshall. David.
Thank you, Jim, very much. Thank you, everyone. Thanks for being here. Good morning. I'm David McKenzie from Marshall Space Flight Center. On behalf of the whole panel, I want to thank the organizers for this opportunity to have a discussion about another one of the ways in which science is supporting exploration. We've heard about a few already this week. Specifically, we hope to entice you with a science problem, one that affects more and more of our technology on the ground, in the air, and in space. Its complexity is part of what makes it fascinating. That topic is space weather, and the people in this room, all of you, are a combination of customers, end users, and problem solvers. So we're hoping to enlist your help because it really does affect all of us. It will not surprise any of you that the space environment is very hostile. Radiation in the form of extreme ultraviolet, X-rays, gamma rays, and energetic particles can be damaging to electronic systems, including spacecraft systems, and certainly can be harmful to human explorers. We'll see if this button works to go to a movie. If it clicks again, maybe the movie will run, but this is an eruptive flare on the surface of the sun. It's Earth-facing, and you'll notice all that snow that's hitting the camera. These are charged particles that are interacting with the detector. In this instance, there was no lingering damage to the instruments. They're designed for this kind of event in mind. But upset events do frequently happen. Communications have been interrupted, spacecraft have been damaged and even lost at costs of many millions of dollars. I'm not going to spend all the time looking through these effects because the list is quite lengthy. But space weather effects range from bulk charging and irradiation, induced electrical currents, to increased atmospheric drag, that one's a real booger, to ionospheric disturbances, GPS modulations. It goes on and on and on. And without going too deeply, you can already appreciate how spaceflight and exploration can be impacted. The heliophysics community have been studying the science of space weather since long before the space age, and we've learned a lot about the causes and effects. But I will assert, and this may be the first controversial thing I say today, that much of what we know is qualitative. A predictive understanding still eludes us in many regards. We're not going to close all the gaps in this 40 minutes. Our aim today is to introduce the topic, highlight some of the ways that science is clearing the way for exploration, and maybe find some ideas for collaborative problem solving. So with that said, let me introduce our panel. I'm David McKenzie, as I said. I'm the Deputy Manager for the Science Research and Projects Division here at Marshall Space Flight Center. Our division performs research in earth science, astrophysics, heliophysics, planetary science, and data science, as well as project management and test engineering support. My research has mostly focused on observations of solar flares and the magnetic structures that produce eruptions in the sun's atmosphere. Sitting next to me is Dr. Nicole Duncan. She's a strategic planning manager within the Civil Space Strategic Business Unit for BAE Systems, where she oversees the division's strategic plan, spearheads special projects, there you go, and drives development of advanced technologies. She got her PhD for research on particle energization and transport in solar flares. Nicole has also chaired NASA's Space Weather Council and served on the White House's Space Weather Advisory Group. On the far end is Professor Gary Zank. He's a University of Alabama trustee professor and holds the Aerojet Rocketdyne Chair in Space Science. He's a director of the Center for Space Physics and Aeronautics Research here at UAH, and also chair of the Department of Space Science at UAH. Gary's a member of the National Academy of Sciences and a fellow of multiple professional societies. Gary's research specialties are space and solar physics, plasma physics, and computational physics. Dr. Teresa Nieves Chinchilla is a research scientist in the Heliophysics Science Division at NASA's Goddard Space Flight Center, where she currently serves as the director of the Moon to Mars Space Weather Analysis Office. She's also the NASA project scientist for the Solar Orbiter mission, a collaboration with ESA to explore the sun's atmosphere, and an adjunct professor at the Catholic University of America. And Dr. Catherine Whitman is a research scientist at NASA's Johnson Space Center in the Space Radiation Analysis Group. She has expertise in the subject of solar energetic particles and galactic cosmic rays, energetic particles that impact the space radiation environment. Katie's involved in space radiation operations and space weather research to operations and operations to research efforts, the R2O2R, with a focus on the methodology and validation of solar energetic particle prediction models. So some of our panelists are going to show charts, so let me ask you to bring up Nicole Duncan's slides first, and we'll get a snapshot of the systems. That big green button.
Okay. All right. Thank you, David, for that introduction and that great overview as well. And thank you to the AAS for inviting us here for these series of very intriguing conversations. So this past May was the biggest event, space weather event, that we've had here on Earth for the past 20 years. It's called the Gannon Storm. You can see some photos of auroras over some agricultural equipment there in northern Minnesota. And one of the things that was really surprising about the Gannon Storm is that one of the most impacted communities was the precision farming community. And so this community uses GPS to maximize how they plant crops within their fields. And they do this to sub-centimeter level precision. During the storm, which happened during planting season, they were having GPS errors around 10 to 30 feet. So this really decreased the amount of crops that they were able to put into a certain area. And some people who have been watching this speculate that the economic impact is well within the hundreds of millions of dollars to farmers. And this is surprising to a lot of us if we were to go back 20 years when the last very large space weather event hit Earth. I know certainly to me it would have been surprising. And that's because no one could have really predicted that precision agriculture would be a big space weather user group. And if we fast forward to 20 years in the future, as we look at building permanent human settlements beyond low Earth orbit, we have to ask the question of who will these new user groups be? And what technologies will they rely upon that are susceptible to space weather? Will we have the measurements, the models, the tools, and the forecasts to be able to support them? Because the level of automation and the precision that automation is occurring in those modules are probably going to exceed what our precision farmers experience today. And it'll be in an environment that is a lot less well understood than the Earth-Sun environment is today as well. So one of the least impacted user groups from that big solar storm in May was actually the electric power grid. And that is actually pretty surprising probably to a lot of you who follow space weather, because that's one of the big things we talk about is potential impacts to the grid. And one of the reasons why they were less impacted is because of long-term planning. And so they're one of the first user communities who were to recognize the risks of space weather and have been working hand in hand with the science and the operations community to build very robust plans for when the next big solar storm happened. But their history is not without incident as well. It was really in 1989 when a big solar storm took out the power grid, the Hydro-Quebec power grid for about 9 hours, and also damaged a transformer at the New Jersey nuclear plant, that the power grid user community really realized the impact that this space weather events could have and really started in earnest a lot of their mitigation planning. So we all know that analogous failures in space will come with much longer remediation times at much higher dollar costs, and then also perceptual costs as well. So as we look at human exploration today, and as we move to what is, a 20-year or perhaps more distant future, how do we make decisions today and tomorrow about what science to fund and how to navigate to that future without similar types of incidents? And so the science community, by and large, uses these decadal surveys that are put out by the national academies. They're done every 20 years. This is the 2013 one. We're eagerly awaiting one that's supposed to come out this year. And these are community-level reports that are put together. You can see in the center an analysis of the space weather gaps that was fed into this report. And this works very well for most of the science communities. However, the challenge with space weather is that we see that the needs of space weather are rapidly evolving as our technological society rapidly evolves. And we certainly saw this within the past 10 years. A great example of this are the rise of mega constellations and just the general proliferation of spacecraft in low Earth orbit. And as that community's needs became more apparent, that's really driving the science that we're looking at doing today, looking at what the neutral density is in the thermosphere and how space weather might regulate and modulate the micrometeoroid environment and the debris environment in those altitudes as well. So the human exploration user community was very recently surveyed for the very first time in the 2024 Space Weather Advisory Group User Needs Survey. And you can see that on the far right-hand side. That's one of the committees that David mentioned that I have been on. And so that user needs survey is meant to go hand in hand with the decadal from the science community. This is really the voice of the user community. And so users from the human exploration sector, both from government and from commercial entities, were all surveyed to produce this report. And so I'm going to leave you with a call to action. And that is, in the next few years, the SWAG will be refreshing this report. And it's a great opportunity for those of you in human exploration, or maybe even other sectors, to get involved, to raise your hand, to have your voices heard, so that way, as the nation comes together and decides what science needs we need to fund tomorrow to enable the future, we have that full consensus of what the community needs. Thank you.
Gary, let's have you go next.
There we go. So I didn't worry about putting up slides. And so Nicole sort of put together a couple of points that I think are worth elaborating on. The first is that the idea of both forecasting and predicting space weather is incredibly hard. Why is that? The system at which one is looking at is just an incredibly stochastically driven system that to some extent defies the easy elucidation of simple drivers. Obviously things like solar flares, coronal mass ejections, and so forth are critical and provide this large-scale input into the system. But associated with that are a set of very, very complex physical processes that have to be understood. These range from the understanding of the nature of turbulence, which is responsible for scattering these very energetic particles. It is also responsible for generating the very energetic particles themselves, whether in the vicinity of solar flares via processes that we don't fully understand. Perhaps it's solar flares. It may be associated with reconnection kind of events where the magnetic field undergoes a topological change, and in doing so liberates a significant amount of energy. In the vicinity of shock waves, for example, you have particles that induce this very strong magnetic field fluctuations that effectively ping-pong energetic particles back and forth across a fast-moving shock wave to produce very high-energy particles. And capturing those kinds of physical processes is exceedingly difficult. Turbulence, as most of you I'm sure know, is a largely unsolved problem even in the atmosphere, which is relatively simple by comparison. It doesn't have a magnetic field that governs and mediates much of the underlying physics. Then there's how these particles actually propagate in this kind of turbulent medium, and one of the sort of great outstanding research problems is how these energetic particles can cross from one magnetic field line to another. It sounds like a simple, relatively trivial problem, but it's one that's defied both analytic and computational analysis for 30+ years. And the reason that's interesting is you can put a spacecraft in one location and you can see a flare go off in that particular direction, and you can be sitting with a spacecraft almost 180 degrees away from that region longitudinally, and you will still be subject to very strong burst of radiation. So the underlying physics is extraordinarily complex, and it was only probably in about the early 2000s that we began to develop physics-based models of how you might expect the radiation environment to develop. And this required a complex compilation of how flares initiated coronal mass ejections, how these propagated through the interplanetary medium, how they accelerated particles, how those particles responded to turbulence in the interplanetary medium, and how they propagated from there. And all of that required state-of-the-art, cutting-edge kind of modeling, theory, simulations. And so there's a very strong need not only for those kinds of predictive-based models to further our understanding, but at the same time also possibly probabilistic-based models in which you can utilize a variety of different factors, different metrics, if you will, that allow you to begin to predict what you might expect to see. And so that is a second ongoing area of research, and to some extent both of those are now also being very heavily mediated by the introduction of both artificial intelligence and machine learning techniques that can either use these very, very large data sets to try to extract some kind of predictive signals or patterns that underlie the nature of the shock propagation, of the energetic particle population, and so forth. And so while forecasting and predicting are at a promising stage, we're probably a good decade away from being able to make reliable forecasts. And so one has to then begin to explore alternate mechanisms. And so a large amount of energy is being invested in understanding what the response of materials should be to energetic particles. And so we've become involved recently in a center of excellence in which the primary role is to really understand the geospace environment and what that composition can do in terms of its impact on different materials that you put into satellites, that you use to shield astronauts, people on the space station, and so forth. And that may be a mechanism that is probably most promising currently for extensive investment. So I'll stop there and let everybody else have their turn.
Okay. Can you hear me? No? Yes? Yes. Okay, perfect. Thank you. Thank you very much for inviting me today to be here. It's an honor and a pleasure to share this table with my panel mates and to share with you and to have the opportunity to share with you what we do in the Moon to Mars Space Weather Analysis Office. I came to this office back in May with the storm that Nicole was describing, and it was a dose of adrenaline. But during this time, one of the things that I did is to go back to the mission statement of this office. And I want to bring this here because this mission statement is very well aligned with the NASA mission statement to explore the space, to push the boundaries of the knowledge by exploring the space. And this is what we do in our office. We support our NASA missions to do the job, and by doing assessment of the space weather. And we also work with the community, with the scientific and operational community to do the transition from research to operation, operations to research. So, and this is what we are. So we aim to be the twos in the research to operation, operation to research. So we work, and it's not obviously a boundary, it is an area where we work with many in the community. Our partners are in the Heliophysics Science Division, is the Community Coordinate Modeling Center, CCMC, and we work very close with them in the transition from the research to operation. CCMC is in charge to ingest the data coming from the research community, and what we do is to perform a real-time analysis every single day, 15 hours per day, 7 days per week. And we do this analysis with the models that are in production mode, and we perform our assessment of the space weather. And in this exercise, we provide the models when they are in operative mode. We provide these models to the operational community, to the SRAC, and to the SWIPC NOAA, which are in charge of the space weather alert and warnings. So at the same time, we close the loop by serving in the transition from the research to, from the operations to research. We collect all the information we perform every day, and we catalog, and we wrap this exercise, this analysis, and provide this information to the scientific community to perform more in-depth analysis and investigations related with these events, this analysis. And this is very important, and we have a human in loop because there are always scientific emotions that these humans are collecting and providing as part of the analysis. And in this exercise, we are always very well aligned also with the Pro-SWIFT Act in 2020, where it was called NASA to enhance the knowledge of the space weather and provide support also in the development of the capabilities for the space weather forecasting. At NASA here in our agency, we also work in very operative mode. We provide support in our missions. We perform anomalies reports in the space weather assessment to any mission that has any problem or anomaly. I brought these examples here, Chandra X, which since it was launched 25 years ago, is developing strategies to provide, to avoid the degradation of the CCD cameras, and we are providing the support to develop these strategies. So we also provide support to James Webb and in the observations and how they are affected by the solar radiation in the telescopic and astrophysics observations. And we also provide real-time assessment. One case that we always like to bring is the Integrity helicopter when it was landing. Simultaneously to the landing activity, it was a flare that it was apparently directed to Mars, and in our office we were able to perform the evaluation of the activity and provide the green light for the landing. So obviously, I'm not going to talk a lot more because Kathy is here and she's going to talk about how we are supporting to SRAG in the International Space Station and preparing our office for the future Artemis mission. And in the human in loop, and Gary was talking also about this, we are mostly focused in two transients in the solar wind: solar flares and coronal mass ejections. These are two solar transients happening, we don't know when, but they are happening right now. We are in the maximum of the solar cycle 25. We had the May storm, and we had a few weeks ago another storm that I hope you enjoy, the Aurora. Both transients are very dangerous for human exploration. While coronal mass ejections are big explosions that dominate and change the global magnetic field of the heliosphere, solar flares are tiny, tiny, tiny explosions, but they are the main source of the energetic particles. Both together in the heliosphere can be unpredictable, and these are challenging our analysts in the office. And I'm not going to go more here in detail, just to bring that we have been working in the last 10 years very well in the community and among the agencies and international partners to prepare for our societies for storms like May storm or October storm. But we are not enough prepared for the future human exploration. In our office, we are working with what we have. And what we have in the deep space is solar heliospheric or planetary missions. Not all of them are operational for space weather forecasting. This is an example. Our exercise is to monitor the whole 360 degrees in the heliosphere using, in this case, for instance, now in October, we were using the low latency data, which is not for forecasting, but is almost real time. We were using this data to monitor the 360 degrees of the heliosphere. And we are doing the same with robotic missions in Mars and with MAVEN also. And this is part of our collaboration among all the missions in the agency and all the centers in the agency. And I'm going to just leave it here. I'm going to introduce briefly the team. But we work with the scientific community a lot in the post-validation of our analysis. Once we deliver our analysis to the scientific community, we are also opening the door to them to come back to us and to work with them in this analysis, and it's part of our work with the scientific community. And I'm going to leave here just the 9 team members. We have people specialized in anomalies, those working in validation, some of them working very close with SRAG, and these are very cool guys. Thank you.
Thank you, Teresa. Katie?
Okay, hello. My name is Katie Whitman. I have some slides. There we are. All right. I'm from the Space Radiation Analysis Group, or SRAG. We're at NASA Johnson Space Center, and we support mission control. Let's see. So I just wanted to introduce SRAG a little bit in case you weren't familiar with us. Our mission is the protection of humans in space, protection of astronauts. We're not in charge of protecting hardware from radiation effects, but we can provide space weather information to the hardware folks so that they could be aware of the environment. And we have a certain philosophy that's called ALARA, and so that is as low as reasonably achievable. So we want to reduce the dose that astronauts get from any sources while also accomplishing the mission. We do that in a wide variety of ways. Like I said, we support mission control, so this panoramic picture here is some of our console operators watching the splashdown of the Artemis 1 mission. That was a really great test activity where we had people on console 24/7 supporting the mission as if there were really humans on board, so that we could test out. We haven't done that in a while. ISS doesn't need quite that much support, so we are testing that out for upcoming Artemis 2. We also have a lot of instrumentation that's on board. Anywhere that astronauts are, we have dosimetry instrumentation measuring the environment. And we also do a lot of vehicle analysis. We help within the vehicle designs to ensure that the shielding is protective to our standards for radiation protection. This is just to show you where we sit with respect to mission control. So there's the ISS mission control at NASA Johnson, and then below that is our side room, or like a windowless room on another floor in the same building. And we're actually we're considered like health support. We interact with the surgeon and the biomedical engineers, and we provide advice to the surgeon, and then the surgeon brings it up to the flight director. The sources that we are most concerned about, we deal with all sources of radiation in space, but that the astronauts might encounter, even, I don't know, like when the eclipse was happening, we tell them, special glasses that they should wear and give advice about things like that for viewing the eclipse. So all kinds of radiation. But mainly, we are concerned with galactic cosmic rays, which are this constant background source of energetic particles that come from all parts of the galaxy and into our heliosphere. And that's sort of a constant background that we kind of have to live with and mitigate in different ways, but it's hard to shield against. These are very penetrating particles. We are concerned with the trapped radiation belts. Mainly astronauts going to the moon or elsewhere will experience those on the outward or inward coming trajectories, but once they're out going towards the moon, they're not going to experience radiation belts. The astronauts on the ISS do encounter them, and they're quick, and we just kind of live with them. And then the solar energetic particle events. So these are the events that, we've all been talking about, that Teresa has talked about, and Gary has talked about, that can be eruptions in the sun that sudden blasts of energetic particles to Earth or wherever astronauts may be. And those we can actually shield against. If we take actions soon enough, we can build shelters and astronauts could go inside and be protected, and we can reduce dose that way. Just the spaceflight environments that SHRAG is concerned with right now is the International Space Station. We have humans there. Out in free space when we're going out to the moon, and then also eventually on the planetary or lunar surfaces. SHRAG monitors the space weather environment all the time. We also get information from NOAA SWPC and from the Moon to Mars Space Weather Analysis Office constantly. I think we're like constantly communicating with you guys. There's constant chatter with M2M about what's going on in space weather conditions. And we look at all of the sources of space weather that we can to keep up our awareness. We also put radiation, like I said, radiation monitors everywhere that humans could be. The ISS is outfitted. All of the modules have different detectors in them. And they even have alarming capabilities if there were to be some kind of radiation event. And the astronauts each carry their own little dosimeter. You can see the astronauts are holding their little personal dosimeters, and that's how we track the dose that they receive through their missions and their lifetime. And lastly, we've been embarking on space weather forecasting. As Gary said, we are nowhere near reliable forecasts right now, but we have to start developing the tools to allow us to look at the forecasting that we can do, validate it, and see where we need to improve. And so working with the Community Coordinated Modeling Center at NASA Goddard and the Moon to Mars office, also at NASA Goddard, we've developed these SEP scoreboards. They're publicly facing. Anyone can go look at them. I don't know if I put the links there. I've been looking at a SEP event that's been ongoing for the last couple of days, sort of tracking it on the scoreboards. And there's actual real-time forecasts coming in from some of the models that have been onboarded there. And we are then doing validation of these real-time forecasts, the way that we use them in operations to see how they work. So it's not just theoretical literature validation, but models actually running in real time. So that's what I have for today. Thank you.
Thanks, Katie. So we got this session started a little bit late because of the great discussion that was going on before. So I want to give time for the audience to have any questions before I ask any here. There's one up on the left and one in the middle.
I'll get the one in the middle, you get the one on the left.
It's a race.
Why don't we go to the middle one here first? Hang on, try it again. It should be on. Check. There we go. They got it.
Okay, so can you tell me about like what kind of research are you guys looking into on like the biological effects of space weather? I'm doing a class project on research, and what I've chosen to do is how it's affecting like the environment and specifically like migration of like different animals that use like magnetic fields to navigate and stuff. I'm curious if you've looked into anything like that to see how that applies to like applying this to humans. So like if you're looking at the biological effects of space weather on different organisms, maybe we can transfer that, stuff like that.
All right, so I'll take that. Mainly we're interested in how radiation dose leads to health effects. And so this comes from a lot of studies, animal studies. And like, okay, this is not my field of expertise at all. Okay, I did physics, but we have people in Shrag who are radiation biologists, and they work on calculating the risk to humans from the radiation dose that they can receive. And the way that they get this risk is they look at all kinds of studies, like animal models. So often it's mice or some other kind of animal that are put into some kind of particle accelerator and given dose of certain particles, and then see what kind of impacts that they have. So we don't look at things like migration patterns of birds or stuff like that. It's really more focused on how a specific radiation dose may impact the long-term health effects of humans. So I don't know if that answers your question, but yeah.
So I don't know whether this is a particular answer of interest to you, but birds and so forth tend to follow the Earth's use the Earth's magnetic field to migrate and at least as far as I understand. I'm not a biologist. And so you might expect then that if you had severe disruptions to the Earth's magnetosphere as a result of geospace storms, so for example, these big coronal mass ejections that we were talking about, or even, so if they impact the magnetosphere, you might find that the whole thing starts shaking. It also depends on what the magnetic field carried onto the Earth's magnetosphere, how it's oriented. If it's oriented in a certain direction, you can initiate very large reconnection events that drive things called substorms. And they also have a very disruptive effect on the Earth's magnetic field. So while you might find that there's no long-term difficulty with birds or any other animals that happen to use the Earth's magnetic field as a compass to navigate, you might find that there's a correlation between their inability to go in a straight line and geostorms, for example. So you may want to look at extensive, probably, data sets related to that. We've got them at least in we've got those data sets, at least in the space field, in the space physics community, but I'm not sure if you've got those extensive kinds of data sets that might allow you to determine whether there's any kind of correlation. But interesting thing to look at.
Can you hear me? Okay. Hi, y'all. Thank you so much for doing this panel. My question is, so I'm actually a physics student, and I'm interested in doing exactly this kind of stuff. So could you give some more specific examples of kind of where you're kind of lacking in terms of the need to do real-time space weather forecasting and understanding like the models of solar activity? Can you kind of give more specific examples of things that students like me should learn and help you guys with?
Fantastic question. And so why don't we, each four of you do it? What's the top one or two items on your wish list and why? And feel free to consider not just near Earth, but also Moon to Mars and beyond, to infinity. Okay. Who wants to go first? That's the spirit.
All right, I'll go first. So I think when it comes to human exploration, one thing that the conversation is really centered around are these direct effects. Like we're talking about radiation that's directly from the eruptive events that originate on the sun. The greater space weather conversation has a lot more to do with secondary effects that involve how the sun-Earth environment reacts to space weather. So, for example, the farming example that I gave, that's because the ionosphere was altered by the space weather event that changed how RF signals traveled down to Earth, which then created the discrepancies in position and timing and position location. So, as we're talking about human exploration, I just haven't heard a lot more of these kind of secondary concerns. Same thing when you talk about the power grid on Earth. It's because of the geomagnetically induced currents in the Earth's crust, not because of the particles that are actually coming down. So I think I would really like to see more research done into the environments and understanding how those environments then interact with the technologies that we're planning in those spaces.
Okay, so before being the director of this office and taking these responsibilities, I was scientist doing science, and my focus was is still, and doing research in coronal mass ejections. And we are really far to understanding how is the internal structure of this coronal mass ejection, this big, large-scale structure, the global morphology, how they evolve, and the interaction with the ambient solar wind is affecting to this internal structure. And we care about the internal structure because when they arrive to Earth, they are the main responsible of the reconnection with the magnetosphere and opening the magnetosphere gate to these energetic particles. So we need investigations in order to develop more physical, fundamental models, going to the basics, to the principles, understanding better or developing these models. And then we need, obviously, more data analysis, and we need more research in the understanding the impact of the evolutionary processes on these structures. Mm-hmm.
Okay, so for space weather prediction, at least for solar energetic particle prediction, which is what I'm most familiar with, we have general relationships that are predictive, like how strong a flare is or coronal mass ejection, and we can come up with these statistical, models and get a kind of idea of what will happen next if we happen to see a flare and CME occur on the sun. But there is a lot of event-to-event variability that our forecasting cannot yet capture. Why is one event small and the next one large, even though they have very similar eruptions at the sun? And so we're still struggling to find what are actually the most important predictive parameters. What observations can actually tell us information about those? And we have a lot of data, too, that I'm wondering if we're using to its full potential. There might be signals in that data that we haven't yet focused on that allow us to have more predictive capabilities than we're taking advantage of now. So that's kind of where I'm thinking. Thank you.
So for me, space weather is really an end product. What's really interesting in many respects is the underlying physics, space physics, and there is sometimes a tendency, and it's an understandable tendency, to kind of mix the two together. But if you're wanting to do the kind of predictive models that Katie and Teresa and possibly even Nicole have been talking about, you need to figure out what the underlying physics is that drives that drives space weather. And as I described very briefly, it involves a large amount of computation You need to be able to solve these very complex systems of equations that you think, in part, describe the physics of just the propagating shock waves or the formation of solar flares. You need to try to understand the physics underlying the energization of particles. It's been I guess, cosmic ray acceleration, how cosmic rays reach their energies has been to some extent a problem of now over 100 years after the first balloon flights over the Alps. It's partially solved in one sense, but certainly not solved fully. And how that translates to solar energetic particles is quite unknown. So it's important to try to build fundamental physical models based on science if you're trying to do any kind of predictive understanding. So, for example, one of the things that hasn't been mentioned are these, except for one event that we had that was the strongest in 20 years, are these huge historically significant, like I think 1952 event, there's the Carrington event, where they produced, where solar energetic particle events were so outrageously large that, estimates of what it might have done to the economy run into, the many, many, many billions of dollars damage. And you can't get at those, sort of 1,000-year or 100-year events unless you have a model that allows you to actually predict that. So we're at a point in terms of modeling where you can begin to predict those kinds of events and what you might expect to see. And that's the only way an engineer can really design certain spacecraft needs based on that kind of event. So I guess the first thing I would say, or the thing I would emphasize is if you're a physics student, focus, I suggest, on developing the physics underlying those models in order to develop a greater predictive capability. That doesn't mean that the data sets that Katie was alluding to are not important, and they're vitally important. It's just that they're so complicated that it's very difficult to extract information. And so, for example, we've been making efforts to use AI and machine learning. It's becoming quite an industry to try to forecast the eruption of solar flares. But there's a fundamental problem with most of those models. We tend to use things called PINs, which are physics-informed neural networks, where you try to use a combination of physics and data to try to understand what the nature of those data sets is. But we don't actually know the physics to put into that properly, and so we use things like technically force-free magnetic field models in order to try to initiate this in the AI model. And you're kind of starting from the wrong basic physics. So there's an enormous range of basic physics that needs to be done. And if you can identify that basic physics, that will allow you to actually use things like AI and machine learning far more effectively. There's garbage in and garbage out, and you've got to worry about that with AI and machine learning.
So before we get to our next question, I don't want to shortchange you all. We did go on a further one, so go a little on if you want to, and we do want to keep talking. And I also want to remind the online audience that you can ask questions as well. Use the Q&A tool in Zoom. So go ahead and pose anything up there. And do we have another question up in the back?
Yeah, I just had a quick question. How do you envision the space weather scientific and modeling community interacting with commercial companies that are going to be providing services as part of the Artemis campaign?
Yeah, great question.
I may take this, but I honestly don't know the answer. So we are not working right now in M2M. We are not working with the private sector. So I know NOAA SWIPC is working most closely with the commercial sector, with the private sector use the resources to develop models in forecasting capabilities in our site. In my office, we are more close to the research mode. And although there are also private companies developing these tools, we don't work close with them. I don't know if you, in SRAG, do something.
We do work with commercial companies in the sense that they're building spacecraft that will carry NASA astronauts into space, and we work with them mainly on their sort of shielding design, analyzing their vehicles as far as radiation coming through. So we have a partnership with a few of those companies in that way. But as far as beyond that, as the space weather sort of analyses that we do, I don't think we don't engage. Yeah, it seems like everyone maybe is developing their own approach to I don't know, to addressing their own space weather needs. I do think they turn to NOAA though quite a lot.
So I think to some extent the answer depends upon what exactly you mean by working with commercial companies. So in one respect, the Pro-SWIFT Act of 2020, which was discussed earlier, delineates what the roles and responsibilities are of the different government agencies when it comes to responsibility for space weather. And so, as we heard today, the responsibility for exploration falls to NASA, or for NASA exploration falls to NASA, right? So with the CCMC and SRAG providing support to those government-funded exploration activities. Now, NOAA, is charged with providing support to the greater public, companies, individuals, everybody else, effectively, for space weather operations. So if you go to their website, you can see that they serve a number of different types of user communities, and you can sign up for all different types of alerts within that space. And so one of the things that they've been doing is these space weather testbed exercises where they bring together stakeholders from different communities, understand what their needs are, and then move to build the operational capabilities to support them. I'm not from one of the agencies. That's what I understand both is set out in law and what they're doing to address it. Now, I think that there's also been a lot of conversation, particularly within the more recent space weather user groups. So I talked about like the rise of commercial companies who are not attached to a government mission statement, right? Proliferation in LEO, particularly of telecommunications companies, things along those lines, who are developing their own models. And I think that extends to the human exploration community as well. Because there isn't an established capability, what we're seeing is that they're tending to develop their own tools and models. There are smaller companies that take the free and available data that's provided by the government and ingest that into their own proprietary models as well.
Right, I'm aware of some of these companies that are using SBIR funding or other startup funding, data services, data modeling, data science, to do the R2O transition and provide things that can be applied to testbed or CCMC or building their own dashboards. And so I think that's kind of where the question is going. I see it as a possibly fruitful field of discovery.
So, and following up with what David's just said, so we work with a number of companies through SBIR grants, which are focused on basically developing forecasting models. The models that we developed as research models are far too difficult for general use and obviously not optimized for company use. So we've been developing those over a number of years. We've put one particular model onto CCMC, so that's available to the community for specified runs as they want. That's one aspect. Part of this is driven by the need to provide engineering backgrounds for people building instrumentation or building spacecraft. So that will serve that kind of need. That also requires models of how energetic particles can penetrate and damage both components and spacecraft. So that's also an area of particular interest because engineers are beginning to try to use very tailored materials. And so now you can begin to design materials that are going to be resistant to, I don't know, atomic oxygen, for example, for a 10-year period or whatever. So understanding those kinds of backgrounds is quite critical for developing instrumentation and spacecraft, besides simply being able to forecast radiation doses that astronauts or others will be exposed to. So there is a considerable interaction now between the research community, or at least some of us in the research community, and different companies.
We got one more quick one back here.
One more, and then maybe we've exhausted the time.
All right. Thank you so much for this panel. I found it very interesting. In the panel, we talked about how high-precision technologies that rely on systems that feel the secondary effects of space weather are impacted. My question is how we plan to prepare for space weather phenomenon we have not yet identified to understand how to prevent this impact on new technology. Specifically, how accurate are our models, and what are the anomalies that we're seeing in the data that we're collecting as compared to our models?
All right, how good are the models, and
So in the
specifically at
anomalies-
finding the unknown unknowns?
So in the anomalies that we are observing, so we in our office, we receive the anomalies and the request for the report of the anomalies. What we provide is the space weather assessment and the possible causes of this anomaly. The anomalies that we see in the spacecraft can be affecting the navigation, GPS, so depending also of the orbit of these satellites. What we do is provide the assessment of the space weather around the spacecraft orbit, and is part of the job in the other side, in the mission management, to evaluate the final report, to do the final report. But this is what we do. Mm-hmm.
You want to chime in, Katie?
Okay, I'll make a comment. So, space weather forecasting still has a long way to go. I'll just make the comment that we are looking to send astronauts to the moon. We're looking to send astronauts ultimately to Mars. We're going to want to develop models, some kind of forecasting models or environment analysis or something for those locations, which means that we need to have more observations, more measurements. We have to characterize those environments before we send the humans there. So we need to start, thinking about taking measurements in the different lunar environments where we might put our humans and our infrastructure. And then also to Mars, there's different space weather considerations. Our observations taken from Earth aren't sufficient to cover Mars all the time because of our orbit. So we need to start thinking about putting some kind of space weather observatories over there if we want to be ready in the future to have humans in those locations. So that's just what I want to say.
Yeah, I'm glad you touched on that. The idea of Earth-independent operations will require monitoring and measurements at those locations. We can't do it all from here and then model and forecast our way out of the problem. So I think we are being conscious of the time, but thanks for the flexibility to go over. But I think the theme that keeps coming back over and over is a predictive capability. If you imagine all the thousands of ships at sea right now with no capability of predicting the weather, only riding out the storm that has hit them suddenly, or sending your kids off on a road trip across the country with no prediction of what the weather is going to do along the highway. You can imagine the hesitancy to send astronauts or expensive assets out into space without knowing the weather that we're going into. And so this is really the capability that we're hoping to develop over the next few years. So thanks for your time and for your indulgence.
Hi, I'm Pritesh Tiwari. I'm currently a grad student at UAH here, majoring in aerospace systems engineering. I'm originally from Ratlam, India, a very small town, Ratlam, and I look forward to career in nuclear thermal propulsion systems. Uh, I'm really happy to be here in person. This is my first time in person. Before this, back in 2020, when I was still in my undergrad in India, I attended this basically remotely, and I had no idea that I would end up here at UH. I had no idea like what I'll be doing. So I was just, I do remember it was midnight at that time in India, and I was just attending this symposium from there. But we will now take a break with snacks and beverages on the bridge, generously sponsored by Barriers Technology. Enjoy the networking and build new connections. Please come back in 15 minutes for our next session on lunar logistics and mobility. Thank you.